we're often going to translate between these three graphs. And when I say translate, I just mean go back and forth between these three graphs. And we started with some simple graphs that look like that. Nice straight lines. When we wanted to look, or when we want to look at the position versus time, and we go to a velocity versus time, using our velocity equation, average velocity equation equals the change in x over the change in t, which looks very similar to rise over run. What this tells me is if I have an x on my rise and a t on my run, that slope is going to equal my velocity. So I can take the slope of that straight line, and that will give me my velocity, whatever it is. In this instance, pretending this is a straight line, that would indicate it's a constant positive velocity. So for that first segment, let's say that's at t equals 1 second, and this is t equals 2 seconds. At t equals 1 second on my velocity graph, my velocity is a constant positive. Then, for the second second, my velocity instantaneously drops to 0. So my velocity versus time graph would look like this. I can use the same thought process for my average velocity, or excuse me, average acceleration. And that's going to be the rise of my velocity graph divided by the run, which is my time. For this specific graph, the slope here is 0, so my acceleration for the entire time is 0. In summary, XVA. To go from a position versus time to velocity, I need to take the slope. To go from velocity to acceleration, I need to take the slope. I can also go backwards. So I can find the area under the curve. I can take the area under the curve for velocity versus time and get my displacement. So somebody has a question, why the area? I'm going to go back to my average velocity, or excuse me, average acceleration formula, which I said was my change in my velocity divided by my change in time. If I wanted to find my velocity, I'm going to multiply each side of this equation by delta t. So my velocity all by itself equals my average acceleration times my change in time. So now you see that I'm multiplying two quantities. If I go up to this graph and I have this and I have this and I'm multiplying those, if my graph looks like this, that's the same thing as saying length times width. So I'm multiplying the two quantities, the two different axes. And that's going to be true no matter what the shape of this curve is. If it's like this, I'm still doing length times width. This is a triangle, so I have to take half the length times the width, or half the base times the height. If it happened to be something different, like that, I can still find this area under the curve, just not with algebra. For this, I would use the math of change or calculus. I say no. You won't be asked that, but at the same time, you could be asked that. I have seen an AP question where you did have to find the area under the curve, and it was actually a curve. And you can do it as long as you are confident in yourself. Let's see, how was that question? Something like that. And there were these grid boxes on here. So if there's grids on here, all you're doing is you're counting up all of those little boxes, right? Estimating. So it wouldn't be like a free response like that? Nah. I don't think there's room in the current format for free response like that. So yeah, like the question I'm thinking of was a multiple choice. I certainly wouldn't give you anything that messy, but you can estimate. Did I answer the question why we take the area? Yeah, good. So let's go through an example, starting with the area under the curve for acceleration versus time. I'm going to give you an acceleration of -10. And this is 2 seconds, and this is 5 seconds. I think those were the numbers roughly that I had used last class. Okay. So for this time interval, what is my change in velocity? Negative what? How did you get that? Okay, so that is what my acceleration value is. But what is my change in velocity? If I'm looking for my change in velocity and I'm starting here, how do I get from my acceleration to my change in velocity? The area under the curve. And you'll notice that I say under. It's not exactly under in this situation. In fact, it's going to be over the curve. It's from the gradient or the slope line to the x-axis. That's what I mean by under. So I'm going to take this area right here. So what is my change in velocity equal to? I'm going to multiply those two values. This is just a nice rectangle. So my average acceleration is -10, and my time was 5. So my change in velocity is going to be -50 meters per second. Now I'm going to create a velocity versus time graph, unless there's questions. No? Yell at me. I'm going too fast or too slow. My change in velocity. Do I have any information to indicate my starting velocity right now? No. I just made up some random number and then I put it on a graph. I don't know what the situation is involved. So we're going to kind of guess here. If I truly don't know and I'm going to guess, I'm going to make my life easy and start at 0, start at a velocity of 0. and then I would draw that graph. But because you guys are going through this for the first time, I'm not going to do that. Because I can do whatever I want. I can do whatever I want as long as I am representing a change in velocity of -50. So let's say I start at this point right here, which is 30 meters per second. There's my 1 second, 2 seconds. There's my 5 seconds. I am going to go down in the first 2 seconds. In the first 2 seconds, I know that my change is -20. Do you see how my change was -20? I've gone down by 20. And then the next, my change is -30. My time interval is exactly the same. This 2 seconds represents this 2 seconds. This 5 seconds represents this 5 seconds. I have gone from a +30 to a -20. So my delta V, my final, minus my initial, does in fact line up with this -50. If I did do that easy thing that I was mentioning earlier, where I started from 0, I would just go down until I got down to -50, just to show that it's a change of -50. So now I can actually do a little check here. Oh, no. No ruler? Oh, there it is. Okay. How would you describe that slope? Good. Constant negative, right? I know the slope of my velocity versus time graph gives me an acceleration. Is my acceleration a constant negative? Yeah. So it lines up, it matches. So I know that I did it right. Okay. Now, to get my displacement, I'm going to find the area under the curve. For the first 2 seconds, I really made this hard on myself. 20 meters. And then I'm also going to add this little piece here, which is 10 times 2. So that area is going to represent 20 meters. And there is a little tiny bit there, but because we're estimating, it's not going to work out perfectly. So what that tells me is for the first 2 seconds, a little bit more than 2 seconds, my total displacement is 40 meters. So now we're going to go the other way, position, velocity, acceleration. And to do that, I think that it helps to have a Madlib. And the Madlib is the slope starts blank or it goes blank. And our choices to fill in either one of those blanks are going to be 0, positive, negative, constant positive, or constant negative. When you're just starting out, you need a starting point. And this, I think, gives you a starting point. So to test this out, there we go. Yes. So for this graph, it starts constant positive. That's in the positive direction. And because we know that the slope of a position versus time graph is our change in velocity, then we can, instead of saying the slope, we can say the velocity starts constant positive, and then the slope goes to 0, which means our velocity will then go to 0. So our slope, constant positive, our velocity starts constant positive, and then goes to 0. In this case, it's going to happen instantaneously. So I like putting in a dotted vertical line. You don't have to. You can just keep it blank. You can do a solid vertical line if that is the case here. And it's vertical because these two lines are straight. So that means instantaneously that velocity is changing. But it's happening so quickly that we're not able to detect it or notice it. Now, looking at my velocity versus time graph, my slope starts 0, and then it goes to 0. So for the entire time, my acceleration is 0. And here's how it's going to change if we have this graph, where now we have a curve. A curve on a position versus time graph indicates there is acceleration. So now, yeah, let me just redraw this. And then we'll change colors. So now, my slope starts what? Positive. Is it constant? No, I can't fit that on. It's not a constant positive. So it starts positive, and where does it go? To 0. My slope is 0 because it's a horizontal line. Might not remember this, so let me talk about that. This doesn't really have a slope here. I mean, it does, but we can just consider the slope of the tangent line to a curve. So the slope of the tangent line, or the slope of the line at that exact point, is 0. So my slope starts positive, goes 0. The slope of position versus time graph is velocity. So my velocity is going to start positive and go to 0, like that, in a straight line. My slope now, how would you describe that graph? What's that? We don't have any data to say what it does after that. So we would just say starts constant negative, and that's what it is. So my acceleration, which is the slope of velocity versus time graph, is going to be what? Perfect. Constant negative. And this is always going to work. It might take a second, a little bit when you first get started, but it's always going to work. Even when we have really difficult graphs like that. Something crazy. That one looks fun. Let's see. My slope right at the very beginning is what? It is 0. So we're starting 0. And where are we going? Positive. Starting at 0 and going positive. So somewhere positive. I can only take this first section at a time because there's a lot going on here. Or that's not even the first section. This is the first section. Then for the second section, I'm starting positive, and then where am I going? To 0, the tangent line right there. So my starting positive, going to 0. For our graphs, we're going to always assume that these curves are changing at a constant rate, which is going to produce a straight line on our velocity versus time graph. Curves that aren't changing at a constant rate are beyond the scope of this course. We don't have to worry about that. Keep it nice and simple. We're not done. Now, the next piece of the graph starts 0, goes negative.
Negative and positive acceleration and constant positive and constant negative deceleration.
So we won't say deceleration because deceleration, when we use that word, that makes us think of slowing down. And if we have negative acceleration, that does not mean that we're slowing down. So instead, we'll just keep with positive acceleration and negative acceleration, or acceleration in the opposite direction of velocity or acceleration in the same direction as velocity to keep them relative to each other.
Wait, but doesn't it go in the opposite direction when it goes like below the 0? It's not going below the 0, it's going down.
Hold on. So that was for this section, we went from 0 to positive, 0 to positive, then from positive to 0, positive to 0. Now, I just haven't drawn it yet. Now 0 to negative. And now the last little section is negative to 0.
But getting closer to 0 means it's like slowing down.
Yes, very good. As you approach a 0 velocity, this is where we're stopped, or we have no velocity. So for this very brief instant here, this magical moment right there, 2 things are happening. Number 1, change that color, high contrast. Number 1, we have stopped momentarily. And number 2, when we pass through the x-axis of a velocity versus time graph, we have changed directions. What does changing directions look like on a position versus time graph? Actual change in direction. Good. It's that point right there where we change directions. In physics, we just keep it simple. Change in direction. So we were going up, but now we're going down. It is often useful, at least for me, maybe you'll find this useful, to look at your position versus time graph as a ruler or a meter stick. And as you are moving away or up this direction, we're getting away from the zero. And then when we're going down, we're going towards the zero. So you can see the actual literal change in direction. What's our acceleration versus time graph going to look like? Slope of velocity versus time will give us our acceleration. So we start off constant positive, then constant negative for a longer amount of time, and then again constant positive. This one looks like I drew it at 55 degrees, and this one looks like I drew it at 63 degrees. So I should have a greater acceleration for that second one. Again, vertical lines not necessary. You can do dotted lines or no lines, whatever you want. Okay, so my total displacement is a positive 40 meters. So I'm going to start at 0 and then go up to 40 meters. So I'm going to end up right here. What shape is this going to be? Is it going to be a straight line from 0 to 40? Or is it going to be curved? Curved. Concave up, down, left, right, down. How do we know it's going to be concave down? Our velocity starts positive and then it goes towards 0. So we can remember that the slope of a position versus time graph starts positive and then goes to 0. And that represents our velocity. Slope of a position versus time graph is velocity. Good, so we've got that. Our next piece, we can calculate whatever this area is here. And we'll say that's negative 20 times 5. I'm going to just use those numbers. Negative 100. So my displacement needs to be 100 meters in the opposite direction that we were heading in. So that's going to bring me all the way down here to negative 60. And that's what my graph will look like. And this all comes from XVA. I can start with whatever graph I want to. In this case, we started with acceleration. We took the area under the curve to get to velocity and drew that, remembering that it's delta V. Then I can take my delta V to my delta and get my delta X, again, by using area under the curve. To go check myself or to go in the opposite direction, I can take the slope. In calculus, we have different names for these. We have the derivative and the integral.